This study, titled, "Accuracy is Not Agreement: Expert-Aligned Evaluation of Crash Narrative Classification Models," explores how well deep learning models and large language models perform in classifying crash narratives compared to human experts. The researchers, Sudesh Bhagat, Ibni Farabi Shihab, and Anuj Sharma from Iowa State University, focus on the idea that a model's accuracy doesn't always mean it aligns with expert judgments, which is crucial for safety-critical applications like traffic crash analysis. At the core, crash narratives are free text descriptions written by law enforcement officers in crash reports. These provide detailed context about incidents, such as what happened, where, and why. For instance, they might describe a car accident at an intersection or on a highway. The study uses data from the Iowa Department of Transportation, covering over 55,000 crash reports from 2019 to 2020, with many including these narrative fields. The goal is to classify these narratives, specifically determining if a crash is related to an intersection or not, based on labels from the report's structured data. The researchers evaluated 5 deep learning models, including variants of BERT, which is a powerful language model trained on vast amounts of text, Universal Sentence Encoder, or USE, which converts sentences into numerical vectors for comparison, and a zero-shot classifier, which can make predictions without specific training on the exact task. They also tested 4 large language models: GPT-4 from OpenAI, LLaMA 3 from Meta, Qwen from Alibaba, and Claude from Anthropic. These models were assessed against labels provided by human experts for a sample of 300 narratives. One key finding is an inverse relationship between a model's technical accuracy and its agreement with experts. In other words, some models that scored high on standard accuracy metrics didn't match what experts thought, while others, like the large language models, showed better alignment even if their raw accuracy was lower. To measure this, the team used Cohen's Kappa, a statistical tool that accounts for agreement beyond random chance. They also applied bootstrap confidence intervals to make the results more reliable. For visualization, they employed principal component analysis, or PCA, which is a way to reduce complex data into simpler components for plotting. This helped them see how different models and experts clustered in terms of their classification decisions. For example, PCA might show that experts and certain LLMs group together, indicating similar reasoning, while some deep learning models diverge. To dig deeper into why misclassifications happen, the researchers used SHAP analysis. SHAP, which stands for Shapley Additive Explanations, is a method from game theory that explains the output of machine learning models by showing which features, like specific words in the narrative, influence the predictions most. Their results revealed that models that aligned well with experts tended to focus on contextual and temporal cues, things like the sequence of events or time of day, rather than just location-specific keywords. This suggests that effective models need to understand the nuances of human language, not just match patterns. In the introduction, the paper highlights the global issue of road traffic crashes, noting a 9.9% rise in U.S. fatal crashes in 2021 despite safety advancements. It explains how crash narratives are valuable for understanding incidents, such as those in work zones or involving distractions, but manual analysis is time-consuming and subjective. That's why automated tools like NLP and deep learning are being adopted, as they're more scalable and can process large datasets quickly. However, the paper points out that these models often lack interpretability and might not reflect real-world expert opinions, which could lead to errors in safety-critical decisions. The methods section details the data collection and preprocessing. They worked with narratives from Iowa reports, which average about 38 words each but vary widely in length. The ground truth labels came from coded fields in the reports, like the location attribute, to classify crashes as intersection-related or not. The team extracted and cleaned this data to ensure it was ready for model input. Building on prior research, the study references how narratives have been used to identify risk factors and reconstruct scenarios in various crash types. It also acknowledges limitations, such as inconsistencies in how officers write reports or data entry errors, which can affect both human and machine accuracy. The paper's contributions are significant. First, it systematically evaluates agreement between the models and experts using Kappa statistics with confidence intervals. Second, it uses PCA to visually interpret differences, making it easier to see where models succeed or fail. Third, it highlights the trade-off. Specialized deep learning models might have high accuracy but poor expert alignment, whereas general-purpose LLMs, like GPT-4 or Claude, capture expert reasoning better, even with slightly lower accuracy. For example, models like Use showed stronger alignment despite not being the most accurate. Finally, the researchers argue that for tasks in crash analysis and other safety domains, relying solely on accuracy isn't enough. Instead, evaluation frameworks should incorporate expert agreement to ensure models are practical and trustworthy. They suggest using LLMs as cost-effective tools for validation, potentially serving as intermediaries in pipelines that combine automated classification with human oversight. This approach could make crash analysis more efficient and reliable, ultimately helping to reduce traffic risks and improve public safety.